discuss the pointwise convergence and uniformly convergence of the series summation n equal to 0 to infinity x power n on closed interval 0, 1. Okay. Now, as I told you, whenever the sequence of partial sum is convergent, then the series will be convergent. If it is pointwise convergent, then the series will be pointwise convergent. If the sequence of partial sum is uniformly convergent, then the series will be convergent. So first we will write down what is given here. What is Gn of x? See the series, and can anyone tell me what is Gn of x here? What is Gn of x from the series?
X power n.
Yes. So Gn of x is x power n. So write down the nth partial sum. The nth partial sum of the series summation Gn of x is, I will take it as fn of x. Fn of x means what is that? Here n equal to 0 to infinity. So I'll take it as g naught g1, that means g naught of x plus g1 of x plus g2 of x plus so on plus gn of x. Okay, so g naught means x power 0, 1. So g1 means x power 1, g2 means x power 2, g3 means x power 3 plus so on plus x power n. Okay. Now what is x here? X belongs to the closed interval 0, 1. Now can I say this is in the form of 1 plus r square plus r cube plus so on r power? That means is it in GP? Yes. Yes, okay. Now this is nothing but the nth term will be Sn equal to a into 1 minus r power n by 1 minus r. Since here x is in the interval 0 to 1. That means here r value is less than 1. So I'm using this formula. Here a is nothing but 1. Okay, you can see the first term a is nothing but 1. So this will be 1 minus x power. Totally how many terms are there? This is x power 0. Okay, so x power 1, x power 2, 3, so on n plus 1 terms are there. So 1 minus x power n plus 1 by 1 minus x. Okay, but when 0 less than x, okay, 0 less than or equal to x less than 1. Suppose if x equal to 1, what you are going to get here? If x is 1, what you will get? You're going to add 1 plus 1 plus 1 plus 1 plus how many times you are adding? How many times you are adding?
n plus 1.
Yes, n plus 1 times we are adding. So fn of x is nothing but 1 minus x power n plus 1 by x minus 1 when 0 less than x less than, 0 less than or equal to x less than 1, and when x equal to 1 fn of x is nothing but n plus 1. Now I'm finding whether it is pointwise convergent in this interval or not. So that means limit of fn of x, whatever value we are getting, that is nothing but f of x only. So I'm going to apply limit to this. So limit of, are you writing along with me everyone? Yes?
Yes.
So 1 minus x power n plus 1 by 1 minus x, where 0 less than or equal to x less than 1, and this is n plus 1 when x equal to 1. Okay. Now concentrate. So I'm going to apply limit to the first term. I'll just write it here. See, the first term is nothing but 1 minus x power n plus 1 by 1 minus x. I'm applying limit to this. Okay, so when 0 less than or equal to x less than 1 means, suppose if I take x value as 0.1, in the numerator it is limit of 1 is 1 minus limit of x power n plus 1 will be limit of x power 1 by, in the denominator limit of 1 is 1 minus limit of x. See, if x is 0.1, it will be 0.1. If it is 0.2, 0.2. That means whatever may be the value of x, the same thing you are going to get here. Okay, now apply limit to this term. Apply limit to limit x power n plus 1. What is that? 0.1 power 1. 0.1 power 1 plus 1 will be 2. 0.1 power 3. 0.1 power 4. What did you observe here? As the value of n is increasing? As the value of n is increasing?
It is close to 0.
It tends to 0. So that means this will be 1 by 1 minus x. Okay. So I'll write it here. Limit of this is nothing but the first one is 1 by 1 minute. This is nothing but 1 by 1 minus x. Okay. And this is when 0 less than or equal to x less than 1. Next, when n tends to infinity, what about the second term? N plus 1 tends to
Infinity.
infinity. So when x equal to 1, I got it as infinity. Now that means what is this? Fn of x. Therefore, Fn of x, the sequence Fn of x tends to f of x pointwise. Pointwise. On which interval? Can anyone tell me? At which values of x you got the limit here? Actually, the given interval is closed interval 0 to 1. But from 0 less than or equal to x less than 1, we got some constant. But when x equal to 1, is it convergent?
No.
No. Then what we are going to write the limit here as?
Closed 0, comma open 1.
Yes, closed at 0, open at 1. So in this interval, the given, in this interval, the sequence of function fn of x is pointwise convergent. Now, since the sequence of partial sum is pointwise convergent, I can say the series of function summation gn of x, which is nothing but summation x power n, converges pointwise to which value? 1 by 1 minus x, which is nothing but f of x in the interval 0 less than x less than 1, or on closed interval 0 comma open interval 1, you can write anything is okay. Okay, so this is regarding pointwise convergent. I'll just go back. So please write down step by step. If you have any doubt in any step, you can ask me. Okay, so first step we took the series, then we wrote the nth partial sum of the series. Okay, and nth partial sum of the series in the interval 0 to 1, we took it as two subintervals, 0 less than or equal to x less than 1, and when x equal to 1. So this is the first step. Finish writing this, everyone?
No, ma'am.
Yes? Okay, I'll wait. No problem. I'll wait.
Ma'am, can you once scroll to the question also, ma'am, a bit?
Okay, ma.
Yes.
Finish writing first step, everyone?
Yes, ma'am.
Yeah, in the second step, I have just applied the limit to find the pointwise convergent in the given interval. Finish writing, everyone?
Yes, ma'am.
Okay. Okay, then shall I continue with the next bit? What we are supposed to prove? It is we are going to discuss the pointwise convergence and uniformly convergence of the given series. Pointwise convergent is done. Now we are going to check for uniformly convergent. So whenever we are checking for uniformly convergent, the first step is we are going to find pointwise convergent of the given sequence. Here also same thing, instead of series, first we'll check for the uniformly convergence of the sequence fn of x or not. So I'm going to use the condition of the definition. What is that? So we'll take for epsilon greater than 0, consider mod fn of x minus f of x is less than epsilon. So what is mod fn of x here? Mod fn of x is, what is fn of x? What did we take fn of x as? See, which are you going to take the this one? Actually, what is fn of x? This entire thing is fn of x. But we are divided this into two subintervals with 0 less than or equal to x less than 1 is one interval, when x equal to 1 is the other one. But at which place you have pointwise convergent? At or only this place you have pointwise convergent. Here it is not at all convergent. So that's the reason we are not considering when x equal to 1. We will consider directly only fn of x as 1 minus x power n plus 1 by 1 minus x. Is it clear, everyone? Yes? Okay, now fn of x is 1 minus x power n plus 1 by 1 minus x minus. Now, and when fn of x is from 0 less than x less than 1, f of x value we got it as 1 minus x. So I took that value. Okay. Now, so what is the next step? Simplify this. Simplify this. Take the LCM as 1 minus x. You will get it as 1 minus x power n plus 1 minus 1 is less than epsilon. Okay. Now, minus 1 plus 1 will get cancelled. Modulus of x power n plus 1 by 1 minus x. Since x is always less than or equal to mod x, I am writing directly x power n plus 1 by 1 minus x is less than epsilon. Now our aim is to find the value of n naught, which is greater than some value, where n naught is depending only on epsilon. It should not depend on x if it is uniformly convergent. If it is pointwise convergent, it can depend on epsilon and x. But if it is uniformly convergent, it should not depend on x. Okay. Now, so from this, I am going to find the value of n. So what I will do is, I'll write this as x power n plus 1 less than epsilon into 1 minus x. Now I want n value. So what I will do, I will take log on both the sides. Log of x power n plus 1 is less than log of epsilon into 1 minus x. This is written as n plus 1 into log x is less than log epsilon into 1 minus x. Okay, so first write down all these steps, everyone. I want only n on one side of the inequality. The remaining terms I will take it to the right hand side. Finish writing?
Yes, ma'am.
Okay, now I want only n. My aim is to keep n on one side of the inequality and take the other terms to the other side. So I'll write this as n plus 1 is less than log epsilon into 1 minus x by log x. So let n be on the other side. So log epsilon into 1 minus x by log x minus 1. If I take LCM, I will get it as n is less than log epsilon into 1 minus x minus log x by log x. Okay, I got n on the one side of the inequality. But did you get anything? Actually, whenever we say as n tends to infinity means n value should be 100, 200,000, 1 lakh, whatever value you are taking, that condition should be satisfied. That means I want always n greater than or equal to some natural number. But what did you get here? Did you get something n greater than some value here?
No, ma'am.
Yes. No, so that means I didn't get the required condition. Since I didn't get, that means I can't choose any n naught which is greater than for large value of capital N, the condition will be satisfied. That means sequence fn of x is not uniformly convergent. Is that clear, everyone? So we'll just write since n is not greater than some constant k, which is a natural number, sequence fn of x is not uniformly convergent. Okay. So therefore summation x power n is not uniformly convergent. Finished, everyone? Yes.
Yes, ma'am.
Okay, next. Second question. Second question, right on. Discuss the pointwise convergence. Discuss the pointwise convergence and uniformly convergence and uniformly convergence. Discuss the pointwise convergence and uniformly convergence of the given series of functions, summation sine nx by n power p for x belongs to R and p greater than 0. For x belongs to R and p greater than 0. I want you all to try this problem. Okay. You will take what is Gn of x. I'll give you a hint for this. So what you're going to do is you will take Gn of x as sine nx by n power p. Okay. Now, what you're going to do, you're going to check whether it is pointwise convergent or not first. When you're checking pointwise convergent, apply the limit, check whether limit exists or not. Okay, for which value of x it is pointwise convergent, take that particular value as f of x, and next, after proving it is pointwise convergent, you are going to check for uniformly convergent, where you'll consider the same thing what you have done in the previous problem. Fn of x minus f of x is less than epsilon or not. For which particular value of n this condition is satisfied, you are going to check. So I want you all to do this as a homework. If you are not able to do this, we'll discuss it in the next class. Okay. Yes. Now we'll go for the next theorem. Theorem number. Can anyone tell me what is the theorem number? Theorem number 5. Okay, done. So we'll start with theorem number 5. So write on theorem number 5. So that means this is the first theorem in series of function. Okay. So write down this statement. Consider a series. Consider a series summation k equal to 0 to infinity gk of x of functions, series of functions on a set S, on a set S contained in R, contained in R. Okay, next continue. Suppose that, suppose that each GK, suppose that each GK is continuous on S, is continuous on S, and the series converges, and the series converges uniformly on S, series converges uniformly on S, then the series, then the series summation k equal to 0 to infinity gk represents a function, represents a continuous function, represents a continuous function on S, represents a continuous function on S. Okay. Now, as I told you, I gave the statement as it is, which is there in your textbook. In your exam, they can modify the statements and they can give you. Okay. Finish writing the statement, everyone.
Yes, ma'am. Yes, ma'am.
Okay. Now the same statement, I'll just give it in and I'll just explain it another way. So no need to give each and every sentence in the exam. What they can give, they may give that if summation gk is a series of function, okay, and gk is continuous on S, gk is continuous on S, or I'll make a small change. If summation gk is uniformly convergent on S and each gk is continuous on S, then prove that, prove that summation gk is equal to summation gk, okay, summation gk is continuous on S. It is a continuous function of on S we are supposed to prove. Okay, I'm repeating the same statement. What is given? I'm just making a small change. What is given? Summation gk is continuous function on S is given and each gk is continuous on S is given. Then we are supposed to prove that summation gk is a continuous function on S. When each gk is continuous, we are proving the entire series is also continuous. Is it clear, everyone? Yes? Yes or no?
Yes, ma'am.
Now, so we will write what is given first. First what is given? Each GK is continuous on S. Okay, when each GK is continuous, can I say that its partial sum is also continuous? Yes? Once I'll write it here. See, suppose, okay, consider the sequence fn of x is the sequence of partial sum of the series, see, or series of function, anything we can write of the series summation k equal to 0 to infinity gk of x. Okay, so I have taken fn of x as the sequence of partial sum of the series of the function. Okay, now what will be actually fn of x? Sequence of nth partial sum. Don't write this. Don't write this. Okay. What is fn of x? Fn of x is the sequence. Sorry, nth partial sum. Nth partial sum is g naught plus g1 plus g2 plus so on plus gn. Okay. But what is given in the statement? Each gk is continuous on S. Is it given or not? Yes. Yes, is it given that each GK is continuous on S?
Yes, ma'am.
Yes, okay. Now when each GK is continuous, that means G0 is continuous, G1 is continuous, G2 is continuous, so on. Gn is also continuous. That means when each and every function is continuous, sum of all the function is also continuous. That means Fn of x is continuous. That means Fn of x means F1 of x is continuous, F2 of x is continuous, F3 of x is continuous, and so on. All the terms are continuous. So since each GK is continuous on S, I can say that each partial sum, each partial sum Fn of x, okay, Fn of x, which is nothing but summation Gk where k equal to 0 to n is continuous on S. Is this sentence is clear, everyone? Yes.
Yes, ma'am.
So we have just used only one condition which is given in the statement that each GK is continuous on S. Okay. Now, so that means since each and every term, that means F1, F2, F3, everything is continuous, I can say that the sequence Fn of x is continuous on S. The sequence Fn of x is continuous on S. Why it is continuous? Since each and every term is continuous here, the sequence will be continuous on S. Okay, so first condition I have used that each GK is continuous. Next, what is left over? Given that the series of function converges uniformly on S. Okay, that means what is given? The second condition is given that summation GK of x is uniformly continuous, is uniformly uniformly convergent, isn't it? Not continuous. It is uniformly convergent on S. Given summation GK is uniformly convergent on S. Okay. Now, series is convergent. When is this possible? Series is convergent or pointwise convergent or uniformly convergent is possible only when the sequence of the partial sum Fn of x is convergent or pointwise convergent or uniformly convergent. Okay. Here we'll write given summation Gn of x is uniformly convergent on S. Okay. So therefore, the sequence Fn of x is also uniformly convergent. This is also uniformly convergent on S. Okay. Is it clear, everyone? So it is uniformly convergent means we will take let Fn of x converges to some function f of x uniformly on S. I have taken that value as some f of x. That means then summation gk f of x, I can write it as summation gk of x, I can write it as f of x. Okay. But what is that? F of x is continuous on S. Why it is continuous? You can see theorem 1. If Fn of x is continuous at x naught, f of x is also continuous at x naught. We know that here Fn of x is continuous on S. Since Fn of x is continuous on S, I can say, okay, I'll write it in the brackets. This is only for your understanding. Since Fn of x is continuous on S, by theorem 1, I'm using this and I'm writing that Fn of f of x is continuous on S. Okay. Now you can see f of x is nothing but summation gk of x. Summation gk of therefore summation, that means the series is continuous on S. Okay, I'll just go back now. So I'll write step by step here. If you have any doubt in any step, you can ask me. First step, Okay, read the first step and write down. If you have any doubt, you can ask me. So what did we take? We have just taken fn of x as a sequence of partial sum of the series of function gk. Okay, so that means since each gk is continuous on s, each partial sum fn will be continuous on s. Since each term, that means f1, f2, f3, everything is continuous, means the sequence is continuous. Is the first step is clear, everyone?
Yes, ma'am.
Yes. Okay, so first write down first step, then I'll go for the next one. First step is finished writing, everyone. Boys, finished writing?
Yes, ma'am.
Okay.
Yes, ma'am.
Next, we'll go for the second step. See the second step, everyone. In the statement itself, it is given that summation gk of x, that means the series is uniformly convergent. Series is uniformly convergent is possible only when the sequence of partial sum is uniformly convergent. That particular thing I'm taking that it is convergent to f of x. Okay, I took fn of x is convergent to f of x uniformly. Then if you remember after the definition of uniformly convergent, I gave this step. If the series converges to f of x, then it is written as. So by using that, I wrote this one. Okay. Now coming to the third step, since fn of x is continuous on s, by theorem 1, I can say that f of x is continuous on, here just write it as since f of x is continuous on s, that means right hand side is continuous, means definitely left hand side, which is equal to f of x, is also continuous on s. Okay, now write on second and third steps. If you have any doubt in any step, you can ask me.
Ma'am,
Third step you want me to explain. Okay. I think you have understood till here, no? How did I write summation gk of x equal to f of x, Charan?
yes, ma'am.
Okay, next. See, in the first step, what did we conclude here? In the first step, we wrote that fn of x is continuous on s we got. Okay, now by theorem 1, fn of x is continuous at x naught means f of x is also continuous at x naught. So the whatever value of x equal to x naught you are taking, it is continuous. So when fn of x is continuous on any interval, f is also continuous on that particular interval by theorem 1. So I'm using theorem 1 and I'm writing that f of x is continuous on s. Is the sentence is clear? How did I get this one?
Yes, ma'am.
Okay. Now check this equation 1. In equation 1, it is summation gk of x equal to f of x. Now what did I conclude here? Right hand side is continuous, I told. Okay. So when right hand side is continuous and the series is equal to f of x, definitely the series will be continuous on s. We are supposed to prove the same thing. We are supposed to prove that summation gk of x represents a continuous function. The same thing we have proved here. Understood? Okay. Shall I go for the next theorem?
Yes, ma'am.
Okay, next theorem. 1 minute. Theorem number?
6.
Theorem number 6. So write down. Theorem number 6. Theorem number 6. Take the heading as Cauchy criterion. Cauchy criterion for the uniform convergence of the series. They can give you state and prove Cauchy criterion for the uniform convergence of the series. So you're going to be perfect with the statement also. Okay. So write down statement. Let summation n equal to 0 to infinity gn of x. Let summation n equal to 0 to infinity gn of x be an infinite series of functions, on a set S contained in R. Okay. Then it is uniformly convergent. Then it is uniformly convergent on S if and only if for each epsilon greater than 0, there exists n naught belongs to n. Such that summation k equal to m plus 1 to n gk of x, such that mod summation k equal to m plus 1 to n gk of x is less than epsilon for all x belongs to S, and for all, okay, I'll write it in the next line, and for all n greater than m greater than or equal to n naught. So once again, I'm repeating the statement. Let summation n equal to 0 to infinity gn be a sequence of, be an infinite series of functions on a set S contained in R. Then it is uniformly convergent on S if and only if for each epsilon greater than 0, there exists n naught belongs to n such that mod summation k equal to m plus 1 to n gk of x is less than epsilon for all x belongs to S, and for all n greater than m greater than or equal to n naught. Finish writing the statement, everyone?
Yes, ma'am.
Okay. Now what is given? Direct, nothing is given in this. It is if and only if. Okay. If and only if it is given only that this is the infinite series of function. Okay. Next, what is given? Please read the statement, everyone. What is given? Then series is uniformly convergent if and only if this one. So first we will consider the first condition. We will consider that the given series is uniformly convergent and we'll prove this condition. Converse, we'll consider the second condition and we'll prove that it is uniformly convergent. Is it clear, everyone? Yes?
Yes, ma'am.
Okay. We'll start the proof. So first we will consider that the series is uniformly convergent. Before that we will write what is the given series of function, what is nth partial sum of the series, all those things. Okay, so write down. Consider summation n equal to 0 to infinity gn of x is uniformly convergent uniformly convergent on S. Uniformly convergent on S. Okay. Now, what I'm going to do, I will take the nth partial sum of the series. So let the nth partial sum of the series. The nth partial sum is, okay, I'll take directly. The nth partial sum is I'll take it as fn of x. Now what will be fn of x here? G naught of x plus g1 of x, or you can write g naught plus g1 plus g2, anything. As I told you, sometimes I'm going to use with x and sometimes without x I'm going to use. Okay. Now, okay, I took the nth partial sum. Now what is given? What is given? Since summation gn of x converges uniformly, since summation gn of x converges uniformly on S, can I say the sequence fn of x also converges uniformly on S? Yes or no? Can I
Yes.
write this? Because by
Yes.
definition only I wrote this one, I didn't write anything extra. Okay, now finish writing the sentence, everyone? Yes?
Yes,
Yes.
ma'am.
Okay. Now, which implies, can I say that F sequence Fn is uniformly Cauchy sequence? See theorem number 3. Please see the theorem number 3 statement, everyone. What is theorem number 3 statement? If sequence Fn is uniformly convergent, if and only if sequence Fn is a uniformly Cauchy. Okay. Now what did we take here? Sequence Fn of x is uniformly convergent. That means can I say that it is uniformly Cauchy sequence? Yes. This only for your understanding. I'm writing in the brackets by theorem 3. In exam, if you remember the theorem statement, you can say that by the known theorem which states that sequence Fn is uniformly convergent if and only if it is uniformly Cauchy. You can write that sentence. Okay. Now I'm going for the next step. Listen, everyone. I'm just writing the condition of uniformly Cauchy. What is that? For epsilon, for each epsilon greater than 0, for each epsilon greater than 0, there exists n naught belongs to n such that mod fn of x minus fm of x. In the statement itself, it is given n greater than m greater than n naught. Okay. So less than epsilon for all x belongs to s, and I'll take here, just I'm writing the condition. Afterwards, I will use whatever it is given in the statement. Okay. Now this is only by the definition I got it. Now what I will do, I will write what is the value of mod fn of x minus fn of x. 1 minute. I will take another sheet. Okay, now just listen here. See this one. This is nothing but mod fn of x means I'm taking n is greater than m. Okay, so what is fn of x? Fn of x is nothing but g naught plus g1 plus g2 plus so on plus gm plus gm plus 1 plus so on plus gn will be fn of x, and fm of x will be g naught plus g1 plus g2 plus so on plus gm. So when I take fn minus fm, modulus of this, what I'm going to get? G0, G1, G2, Gm, all these will get cancelled. And what is left over? Gm plus 1, 2, Gn is left over, isn't it? Yes?
Yes, ma'am.
Okay,
Yes,
so
ma'am.
the same thing I'll write it here. So what is left over here? Only the terms from, that means for epsilon, for each epsilon greater than 0, there exists n naught belongs to n such that what are the terms which are left over? Gm plus 1 of x plus gm plus 2 of x plus so on. Gn of x is less than epsilon for all x belongs to s, and now I am writing that condition n greater than m greater than or equal to n naught. Okay. Okay. Now actually what we are supposed to prove, for each epsilon greater than 0, please look into the statement, everyone. There exists n naught belongs to n such that mod summation k equal to m plus 1 to n gk of x is less than epsilon for all x belongs to s, and n greater than m greater than or equal to n naught. We are supposed to prove this condition. Did I get the same condition? Yes.
Yes, ma'am.
So first write down this. The converse part we'll do it tomorrow. Okay, so I'll write steps here 1, 2, 3. So first step, second step, third step. So write down this everyone, and tomorrow when you're coming for the class, just see once this proof is the font size is okay. Yes. Just see this proof and come to the class. If you have any doubts, you can ask me tomorrow. Okay. So meanwhile, write down, I'll be taking the attendance. So roll number 1,
Present, ma'am.
2,